of my favorite topics in chemistry, intermolecular forces. It will explain to you a lot of the properties of things that you see. It will explain to you why honey is viscous, whereas water is, runnier. Why geckos can walk, or how geckos can walk on walls, vertically. But to first understand this concept, really, you need to be familiar with these three concepts. Types of bonding, especially covalent bonds. Electronegativity, which is the measure of how much an atom wants electrons, or how strong it can pull electrons towards itself. And the definition of a molecule. As you can see from the name itself, international, right? Between nationals. Inter means between, and molecular, referring to molecules. So the name itself means forces that are between molecules. Right. Okay, so we have learned covalent bonds, we have learned ionic bonds, metallic bonds. So why do we have to learn more types of forces, bondings? Well, because they're different. Okay, so we have intramolecular and we have intermolecular. So what we've learned so far, like covalent bonds, is intramolecular. So here is a great analogy I took off Khan Academy. Imagine you have hydrogen and chlorine. In this case, you have these towels that act as hydrogen and chlorine. So blue is hydrogen and pink is chlorine. And say you sew them together with this green thread. This sewing represents covalent bond. So you put H and Cl together, making hydrochloric acid. It forms one molecule, right, of hydrochloric acid. So you sew them together, you have one molecule. You do that 3 times, you have 3 molecules. And say you want to combine these 3 molecules together using this Velcro. I don't know if you guys know what Velcro is, but feel free to Google. You might see them maybe in like your pencil case. So Velcro is weaker than sort of sewing things together. So if you pull this setup, what you'll have is that the Velcro would give out first. Okay, of course, if you keep pulling, then you'll have the covalent bond break as well. But just like Velcro, intermolecular forces are more easily sort of broken up and then returned. So because Velcro, you can kind of just open and close. So intra means within a molecule. So that's the force that makes a molecule. Okay, and intermolecular forces exist between molecules. All right. If it's still not clear, don't fret. We'll see some examples, and hopefully they'll make it clear. So there's 3 types of intermolecular forces that you need to know. Dipole-dipole, London dispersion, and hydrogen bonding. Okay. This all sounds very fancy, so let's take a look at the first one, dipole-dipole. I think it's the most intuitive to look into, so we'll start with that. Okay. So to get into dipole-dipole, we first need to just have a recap of electronegativity. Just remember that some atoms, in this case the ones over here, are more electronegative than, say, the ones over here. And so what that means is that, let's say, oxygen, fluorine, chlorine, these are atoms that are more likely to pull, that are going to pull electrons away from other atoms. So say we have HBr, hydrogen bromide. Okay, remember we might have drawn hydrogen bromide like this in a Lewis structure, representing the electrons, right? Okay, this guy here would represent a covalent bond. But actually, this is not very accurate. Because bromine over here, bromine atom is so much more electronegative than hydrogen. What happens is bromine will actually pull the electrons closer to itself. It's a bit selfish. Okay, so if this was like a tug of war between ropes, the rope will be closer to bromine. Bromine is stronger. So if you pull more electrons towards you, you will become a little bit more negative. So as a result, there's this side will become more negative and this side will become positive. So now you've created this molecule actually can be represented, almost like a magnet, with one side being, North Pole, South Pole, in this case, one side being a bit more negative and one side being more positive. So there's a polarity. Okay, there's almost like sides. Now, remember if I have say, I have a jar of hydrogen bromide, you're not just going to have, say, this jar of hydrogen bromide. You're not just going to have one, you're not just going to have one atom. You're going to have gazillions of atoms, right? Sorry, molecules. You're not just going to have one molecule of hydrogen bromide. You're going to have almost like a gazillion of them. So these molecules are going to interact with each other. Okay, they're almost going to align in the negative side. So I'll show you here using this picture. So you see the negative side will be attracted to the positive side, right? Remember, opposites attract. So you're going to have this kind of, in a jar of hydrogen bromide, all these molecules are going to interact in this manner. And we usually denote intermolecular forces using this dotted or hashed lines. Okay. And so here you have an interaction or attraction between these four molecules. Okay, so that's the first type of intermolecular forces that exist in any polar molecule, So here I'll show you two more examples of some molecules. So carbon dioxide on the left side here, this is not polar. Okay, not polar. Okay, as you can see, the oxygen kind of have equal strength, so they pull the electrons equally from left and right side. So as a result, this entire shape has no polarity, okay, because it's like symmetrical, right? Here we have water, which has a polarity because of its shape. You can see this side is more negative, and the bottom side is more positive. This side is more positive because oxygen is more electronegative, and the shape is not sort of, like once there's more pull towards the top side of the oxygen. So this carbon dioxide will not have dipole-dipole moment, but water will have. And water will actually have later another thing we learn about hydrogen bonding. So what kind of intermolecular forces might carbon dioxide have? They will actually have London dispersion forces. So let's talk about London dispersion forces. Now, London dispersion forces exist in all molecules, between all atoms, and it's actually best, I believe, described using sort of best shown using a video style GIF. Okay. As you should know, electrons are not static. So here we have two helium atoms, and they have two electrons each atom, and these electrons are always kind of roaming around. They're always circling the nucleus. So sometimes the electrons would just happen to be more on the left side, just by chance. And as a result, if let's say the electrons are more on the left side, then you have a polarity. Then the left side will be more negative, right? And when there's that polarity again, it will attract. So these two atoms will attract. So this is like London dispersion forces can be thought as a temporary dipole attraction. So it's temporary because you can see the electrons will start moving again and then they break apart. Okay. So you can see from this diagram. So let's go back. Okay. So as we saw, London dispersion forces are temporary just due to the movement of electrons. So things with atoms with more electrons will naturally have more London dispersion forces. And as I mentioned again, all molecules also have London dispersion forces interaction between them, even here in hydrogen bromide, but the London dispersion force is being overshadowed by the stronger dipole-dipole interaction. Okay, so it's being overshadowed. So where you will see these the most impact in a London dispersion force is probably in the group 17 in the halides. So you can see here fluorine, chlorine. So this is going down group 17 or group 7. You can see fluorine is a gas at room temperature, and iodine here is solid. Okay, this is simply due to the fact that iodine has more electrons. So more electrons, more London dispersion forces. Okay, now let's take a look at hydrogen bonding. So hydrogen bonding is in all textbooks an example, kind of demonstrated using water. So that's what we're going to do. So hydrogen bonding, as the word kind of suggests, requires hydrogen. So here I have water has hydrogen. It also requires a very electronegative atom. So in this case, it's oxygen. So when there is a very electronegative atom and hydrogen, there's going to be a strong pool of electrons towards one side. So there's a very strong partially negative side. So delta negative, this is the delta sign, and delta positive. So there's a very strong kind of polarity. So what happens? Well, when there's another water molecule, should I just draw another one? Like, let's say, I'm just going to draw actually my own. And if you wonder why teachers tend to draw oxygen in this way, okay, that's actually covered in another topic, the shape of water. And let's say, why is it so small? Okay. Okay, so what happens here? You can see the lone pairs on oxygen is actually going to be attracted to the slightly positive hydrogen. Okay, now this attraction is actually quite strong. So I don't know if it's familiar looking, but this should I, if I can make it a little clearer, maybe by increasing the size, this should remind you almost of a dative or coordinate covalent bond. Almost, not exactly. Almost like it's donating that lone pair to the hydrogen. Okay, so you'll have, here's a better picture. You'll have water tends to be covalently bonded in this manner. And if you've ever played with water, you'll actually notice that if you put the droplets together, they tend to kind of just combine. That's actually because the hydrogen bond is quite sticky. So water do tend to stick together. All right, should we do a recap of all these three? Yeah, we should. Quick recap here. You have dispersion forces, dipole-dipole, and hydrogen bonding. This is in order of strength. So dispersion is the weakest. Dipole-dipole, second strongest. So note as well, you can actually have hydrogen bonding. It doesn't have to be in water. You can also have it in, say, NH3. Okay, so nitrogen is sufficiently electronegative. You can have it in HF, hydrogen fluoride, because F is very electronegative. So you need H bonded to a very electronegative atom such as F, O, or N, so fluorine, oxygen, or nitrogen. And you can see also, again, dispersion forces, although it's the weakest, it can actually be quite strong. So you can see the strength can actually accumulate. Okay, so the more electrons you have, the stronger your dispersion forces. Yeah, so again, dispersion exists in all molecules and atoms. Dipole-dipole exists only in polar molecules. Okay, so molecules where the atoms in it have difference in polarity and the shape is not symmetrical. And hydrogen bonding in molecules containing H bonded to a very electronegative atom. All right, so that's a quick recap of a quick discussion of intermolecular forces. Obviously, it's time for us to jump onto some questions. All right, thanks for listening. So here's some resources that I think would be a lot of fun to watch or read. There's definitely a lot more out there. As I mentioned, it's such a good topic to understand more, the world around you. So definitely do some more of your own detective work. See how far you can go with the concept of intermolecular forces. Thank